Okay, so welcome everyone to this webinar, who is part of European projects of the MSK framework, MSK and Citizen. The project is called PICO, Physics for All, and it's an European collaboration funded by the European Union. This webinar is also part of a series was called Women Exploring the Limits, by our institution. So my name is Giulia Vannoni. I am the project manager of the Center Cosmos, Science and Societies, that is devoted to public outreach and creating and strengthening bridges between science and society. And during these webinars, we invite some of our researchers to talk about their field of research to the general public. So today we have two cosmologists with us. They are two young researchers from the APC lab, Anaïs Widmer and Amalia Villarrubia-Aguilar. And so I will let themselves tell us more about them and their research. Anaïs?
Hello, so my name is Anaïs, and I'm a second-year PhD student at the laboratory APC in Paris. I'm working on galaxy clusters in cosmology, and before my thesis, after high school, I did a class préparatoire. I don't know exactly how to say this in English, but it's an intense preparation for engineering school in 2 years. But after this, I didn't want to do an engineering school, sorry. So I went to the university in Paris and I did my license and my master in the University of Paris. And during my master too, I specialized myself in the physics of the two infinities, so particles physics and cosmology. And then I started my PhD in October 2023 on galaxy clusters.
Amalia?
Yes, hi. So my name is Amalia. I'm a first-year PhD student at the IPC lab in Paris. Before starting my PhD, I did a bachelor in astronomy in the University of Leiden in the Netherlands. And then I did a master's in physics at the University of Zurich. I did a major in cosmology and a minor in computational science. And I've recently started my PhD here in Paris, where I'm working on B mode detection with CMB photons. I'll talk about it a bit more detail later.
Yes, indeed. So let's start from the basics. We said that this webinar is about cosmology. So can you maybe tell us what modern cosmology is, what it studies, where we're at? Anaïs, we start from you?
Yes, I will share my screen. Can you see it?
Yes.
Okay, so cosmology basically is a branch of astrophysics which understands the history and structure of the universe, but with scales beyond the Milky Way. So cosmology, it has very large scales. And in this science, so we study the components of the universe, like the large structures like galaxies or cluster of galaxy, but also the cosmic background, like the cosmic microwave background. And we want to know how the universe has developed and what are these major components and basically what is the universe. So the beginning of cosmology starts in 1950 when Einstein developed his theory of gravity. So it says that gravity is a geometric property of space and time. And here you have the very famous Einstein's equation. But so this theory was a revolution in gravity because before the only theory was the Newton theory, and the Einstein's theory that permits to explain the motion of very heavy objects like planets, stars, but also black holes or galaxies. And after through astrophysics, Friedman and Lemaitre rewrote this equation, but in the case of an homogeneous and isotropic universe. So homogeneous means that the universe is the same everywhere, and isotropics means that the universe is the same in all directions. And this is very important to write such an equation. So this equation describes the evolution of the universe, and it is very important, and it permits to get the standard model, a model which is describes how actual universe, but we will explain it more after. So yes, Amalia will speak about the standard cosmological model.
Yeah, so I'll briefly explain what happened in the very early universe according to our standard cosmological model. So as you might know, the universe started with the Big Bang about 13.8 billion years ago. This marks the beginning of space and time, and so in this moment, all the matter and energy contained in the universe was basically confined into this single infinitely dense point. Then almost instantly after the Big Bang, the universe started to expand and to cool progressively, which allowed to set the stage for everything that followed. In particular, so less than a second after the Big Bang, the universe underwent this very brief period called cosmic inflation. So during inflation, the universe grew incredibly fast, many, many orders of magnitude, in just a fraction of a second. And what inflation did was stretch out the quantum fluctuations, so the tiny ripples of the primordial universe, into much larger fluctuations in the distribution of matter. And Anaïs will talk a bit more about that later. So as inflation ended, at this point, the universe is still younger than 1 second. All the elementary particles that it contained formed this very hot, dense soup called the quark-gluon plasma. And we had to wait about 10 more seconds before photons, so the particles of light, were formed, and then quarks could combine with to form protons and neutrons. And a few minutes later, a few minutes after the Big Bang, primordial nucleosynthesis took place. So during primordial nucleosynthesis, they were nuclear fusion reactions, which happened throughout the entire universe. And what this meant is that protons and neutrons fused to form the first atomic nuclei. So at this point, it was just hydrogen, helium, and very small amounts of lithium. This kept happening for about 20 minutes. And after 20 minutes, the universe had cooled down to the point there that nuclear fusion could no longer continue. What this means is that heavier elements like carbon, oxygen, or iron would have to wait billions of years until they could be formed much later inside the center of stars. So at this stage, the universe was really just hydrogen and helium nuclei. That's the two lightest elements, and they still make up the vast majority of ordinary matter today. And then for the next 380,000 years, it was a bit boring. You had to wait for a long time. It was still a very hot, dense plasma with just these atomic nuclei, free electrons and photons. And so what happened during this time is that photons were constantly interacting with the charged electrons. So they were continuously scattering off of these electrons, which prevented them from traveling freely through the universe, meaning that at that time, the universe was completely opaque. This is a bit like if you imagine trying to look towards something when there's very dense fog, the photons can't pass, so you won't be able to see it, right? So after the universe continued to expand and to cool, and eventually, after 380,000 years, something really exciting happened called recombination. So the electrons could slow down enough to combine with nuclei and to form neutral atoms. And this was a major turning point for two reasons. First of all, you had the first stable atoms that were now in place in the universe. So at that point, it's just hydrogen and helium. And then the other thing that was exciting is that there were a lot less free electrons around to scatter light. And so photons could finally, for the first time, move freely through space. So the photons were scattering, they just scattered off electrons one last time before they were all released into the universe at the same time, and the universe became transparent for the first time. So this scattered light from the very early universe is what we call the cosmic microwave background radiation, or CMB. So that's what I work on. I'll explain a bit more later in more detail. But today we can still detect this CMB photons as a very faint glow that fills the entire sky. And that provides us with a snapshot of the very early universe. So if you want to take it from here, yeah.
So after the CMB emission, the structure's formation starts. So there was a gravitational collapse, which leads to quasars formation. So quasars are supermassive black holes. And then with these black holes, stars, then galaxies, then galaxy cluster forms. And so the universe which is its final state. I mean that the state we know it, so the state of today. And so the structures formations is very important in cosmology because it took a very long time. And when we study at each time, at each age, story of the universe, how many galaxy clusters there was, for example, it is a very important indicator of quantities of dark energy and dark matter, but I will explain it more about the two things after. And I work particularly on galaxy clusters. So galaxy clusters are the most large gravitationally are the most large structures that we know. So they are between 20 or 100 galaxies in clusters. So this is very huge. And their studies is very important to understand the history of the universe. But I will explain it more later.
Mm-hmm.
Okay, sorry.
Yes, no, let's get to this. So what you described is what we call the standard cosmological model, right? This is basically, as you explained, all the things we come to know up until now, right? With roughly 100 years of cosmology under our belts, right? From the 20s. And so this is our scheme, the scheme you work within, but then have we understood everything? Like, do we know how the universe evolves? Do we know our universe, in fact? Amalia?
Yeah, so yeah, before diving into the standard model that we just described is called the lambda CDM model. So before diving into the limitations of the lambda CDM model, I think it's important to take a step back and talk about just briefly what a cosmological model, really is and what it isn't. So scientific models, including the lambda CDM model, they're not absolute truths. They're always provisional. And so you can see a model as a kind of a self-consistent framework, which is useful for describing our observations that we have gathered to date, and make predictions. But any model, by definition, simplifies reality. And at the same time, you want to preserve a certain degree of complexity, which has to be manageable for the people working with the model, and has to allow you to describe nature as you perceive it. But there's always, the nitty-gritty details that you will simplify in one way or another. You can even sometimes have, seemingly incompatible models that coexist, each capturing kind of different aspects of a phenomenon that can be useful to answer different questions. So I don't know, maybe some of you might know that light, for example, can be described as a particle or as a wave. And both of these models are correct in the sense that they're just used to answer different observations. So to go back to the lambda CDM model, it's not the absolute truth about the universe. It's kind of our best working description so far. And it's been really successful at describing most of our cosmological observations. But like any model, it has its limitations. And in particular, for the lambda CDM model, it relies on 3 key ingredients that we currently don't fully understand, which you might have heard of. They are dark matter, dark energy, and inflation. So we can talk a bit more about that.
I would like that. So yes, no, Anaïs, go on. Can you explain a little bit more about these mysterious elements of the model?
Yes. So this diagram represents the content of the actual universe. So as you can see, we have around 73% of dark energy, 23% of dark matter, and the rest is normal matter. So normal matter is basically what you can see around you. And dark matter, I will explain it just after. But dark energy is not really matter, but it's the motor of the accelerated expansion of the universe. So let me explain. At the beginning, so with since the Big Bang, the universe is in expansion, and this expansion is accelerated with time, and we don't know why, but to have such acceleration, sorry, there sorry, so this acceleration is so the motor of the accelerations is maybe an energy, and the scientists call it dark energy because we don't know what it is, but it exists, and there are a lot of proofs of its existence, but we don't know what is it. But I will more concentrate myself on dark matter because it's simpler to understand. So dark matter is really matter, and we can see it only by gravity, but not by light, and this is why it is called dark matter. So here you have one of the proofs of its existence. So in red, this is a curve calculated without dark matter, just with ordinary matter. And so this plot is the rotational velocity of galaxies as a function of its distance from center. And so just with ordinary matter, it decreases when you sorry, when you
When you get farther away.
yes, when you get further of the center, but with dark matter, it doesn't decrease. So sorry, but we measure it that it doesn't decrease, but we don't see the matter. So we can't see by light the result of this, but we can measure it with this plot. And so this difference of velocities enlightened the fact that dark matter can be detected by gravity, but not by light. So, okay, so and dark matter and dark energy are two components of universe that we don't fully understand, but we can detect them. And it's a big question of cosmology because, as you can see on the diagram, they represent the major part of the universe. And the three big question is the inflation.
Yeah, so the
Okay.
third, I'll continue with inflation. The third ingredient of this lambda CDM model that remains poorly understood to this date is cosmic inflation. So I briefly mentioned it in the beginning. Inflation is this very short period of time right after the Big Bang, during which the universe expanded incredibly fast. So the idea of inflation was first postulated as a way to explain some of our large-scale observations, which we didn't really understand. In particular, the first thing that inflation explains is why the universe looks so remarkably uniform. So when we observe the CMB, and we look at regions of their sky that are incredibly far apart, they almost have the exact same temperature. And without inflation, there's really no way for these two regions to ever have been in causal contact. So there's no way for them to have exchanged information and reached this thermal equilibrium. This is the puzzle that we call the horizon problem in cosmology. And the idea of inflation solves this because it says that actually it's just a really tiny, already uniform patch of spacetime that has been stretched at the beginning. And so these two parts that seem to be very far apart actually come from the same patch in which they already had the same initial conditions, which explains why now, although they're so far apart, their temperatures can be so similar. So that's kind of the first puzzle that we can explain with inflation. And inflation also provides an explanation for what we call the flatness problem in cosmology. So the flatness problem is the fact that our observations show that the geometry of the universe is extremely close to flat. What that means is that the total energy density of the universe is really finely balanced between causing it to eventually recollapse or to expand forever. And this balance should be highly unstable. So this means that any tiny deviation from perfect flatness in the early universe would have grown dramatically over time, with the expansion leading to a very much non-flat universe. But inflation, again, can resolve this by stretching space so much that any initial spatial curvature is actually smoothed out or like ironed out during inflation, which would explain why the universe that we see today is so close to being flat, regardless what its initial curvature was. So inflation works really well to explain what we see, but one of the biggest problems is that we don't know what caused it. So I said before, inflation was this period of very rapid expansion, but just to give you an idea of how rapid this expansion really was and how dramatic it really was, basically the universe expanded by a factor of 10 to the 26 during a period which lasted 10 to the minus 32 seconds. What that means is that if before inflation you were sitting a meter away from someone, in just a fraction of a second later, and when I say a fraction, it's a really small fraction, the space between you and that person would have stretched out so much that after inflation, that person would be sitting all the way outside the Milky Way, so all the way outside our galaxy. That's how fast space expanded during inflation. And there's no physical mechanism that we know of that could have driven such an intense, short-lived expansion. So different theoretical models have been proposed by theorists. Most of them involve new physics beyond our standard model. But so far, we don't really have a clear answer of which of these models could be correct and could explain that. And in addition to not knowing what caused it, we have never really been able to observe it directly. So many of its predictions match our observations, which is why the scientific community believes that inflation took place. But we're still looking for a more concrete evidence. And until we find really a direct signature of inflation, it will remain a compelling but unproven piece of our cosmological picture.
And so in all this framework and all these huge mysteries that are left to explain, can you tell us a bit more about your personal work? What do you do? Where does your contribution come in?
Yes. So, as we said before, in cosmology, so there are two main branches. So first, the large structures, and then the CMB, so the cosmic microwave background. And for me, I work on large-scale structures and so galaxy clusters, which are the large structures that we can know, as I said before. And in particular, I work in Euclid. So Euclid is a European mission. So Euclid is a satellite which is in heliocentric orbit, and it sees like in Euclid.
Sorry. My bad. Gone.
Okay. And Euclid observes the sky and in particular galaxy clusters. And in Euclid, I work on validation of the data with comparisons between different surveys and the study of galaxy clusters properties. So Euclid was launched in 2023, and we already have a bit of data. So we have to check this data in order to validate it. I mean, we want to know if there are newly discovered clusters by Euclid, so clusters which are not in previous surveys, but just with Euclid. And we also want to prepare analysis of scaling relations between different cluster properties, such as mass, luminosity of number of galaxies, sorry. And so Euclid will provide a lot of information for each galaxy clusters, and my work in Euclid is to check this information in order to validate it or not. So if, for example, if Euclid see a galaxy cluster at a given position, we want to know if there was already another cluster C at this position by another survey, and if there is another clusters, if this other cluster has the same properties than the cluster seen by Euclid, if they have the same mass, the same luminosity, and the same number of galaxies, etc. And after all, to study the difference, and the final goal is to check if Euclid is a good survey or not in comparison with the previous survey. Yes. And that's it. Yes.
Yeah, so shall I, for me? Yeah, so I briefly introduced the CMB in the beginning and the fact that we can see these very primordial photons as a faint glow that fills the entire sky today. So one of the key properties of CMB photons that we can measure is their polarization. So polarization it describes the orientation of light waves perpendicular to the direction in which they travel. If you don't know what polarization is, that doesn't really matter. That's okay. What's important to know is that theorists believe that during the rapid expansion of space, during inflation, this would have generated two different types of waves in the very early universe. So on one hand, density waves, which are fluctuations in matter, and on the other hand, primordial gravitational waves, which are kind of ripples in space-time itself. And so these different waves in the early universe polarized the photons in the early universe in different ways, and these different polarizations show up as different patterns in the CMB photons that we observe today. So on one hand, the density waves, they would have produced a pattern that we call E-mode polarization in the CMB, which you can see in the picture, or the figure on the left at the top. So these E-modes, as you can see, they're very symmetric in every direction. And on the other hand, the primordial gravitational waves, they would have produced E-mode polarization in the CMB as well as B-mode polarization patterns. And this B-mode polarization pattern, which you see at the bottom, has this kind of characteristic swirling or curling pattern, which allows us to distinguish it from the E-modes. And that's what we're looking for. So these B-modes, they can only be produced by the gravitational waves from inflation. And this is what makes this B-mode polarization pattern in the CMB a unique and direct way to test inflation. So I just said that we hadn't been able to observe inflation directly, but that's why we're looking for these B-modes, because that would be the first time that we're able to observe directly the effect of inflation. So detecting these B-modes is really challenging because it's a very faint signal. It's much weaker than the dominant E-modes. And on top of that, our own galaxy also emits polarized light, which can mimic the B-mode pattern in the CMB. So to extract really the B-modes from the CMB, you have to carefully remove these foreground emissions and then map the CMB polarization with a lot of precision. And that is what the group that I'm part of is working on. So the idea is to develop computational tools to isolate the faint CMB signal from all the foregrounds, and then create detailed maps of the CMB polarization, and then using statistical techniques, measure this B-mode polarization pattern, and in particular, its amplitude. Yeah, that's something I didn't talk so much about, but beyond just detecting these B-modes, we also want to measure their amplitude, or basically their strength. Which will allow us to validate or invalidate some of the theoretical models that have been developed to explain inflation by theorists. So the strength of these primordial gravitational waves, and so the strength of the resulting B-mode polarization, depends on the specific details of how inflation happens. So in particular, how fast it happened, what type of energy field drove it, that sort of thing. And so we parameterize this strength by a parameter called the tensor to scalar ratio in cosmology, which is denoted by the letter R. And different models of inflation predict different values for R. So what we want to do is try to measure the value for R, and that will allow us to discriminate between models that do describe what we see in the universe and models that do not describe, do not match our observations, basically. And that will allow us to maybe learn a bit more about how inflation could have happened and what kind of model is behind inflation. Yeah.
Thank you. I'm guessing there will be some questions, but before we open to that, so we both talked about data analysis basically, and getting new data to to progress in the knowledge that we have about our cosmological models. So my questions now would be, can you tell us a bit more about the instruments, the new and upcoming instruments that you will be using in your research? Maybe we start from Amalia. Anaïs, is everything okay? Yes. I don't know. Do you have something about?
Yes, we have it. So, okay. So for me, I will talk about the instruments to observe large-scale structures since it's my work. So they are both a ground-based telescope and satellites. So for the ground-based telescope, I took as an example LSST, which means Legacy Survey of Space and Time. So is a ground-based telescope in the Rubin Observatory located in Chile, but it's under construction, and it will provide hundreds of images of the South Hemisphere sky every night during 10 years. So LSST will permit, of course, to observe large-scale structures, but also stars, planets, and a lot of celestial objects. And then for the satellites, I took Euclid as an example because I'm involved in this mission. So as I said before, Euclid was launched on July 2023, and it is in heliocentric orbit, and it will provide one of the largest galaxy clusters catalogs with around 100,000 clusters over more than a third of the sky. So it will be a very huge data, and we have to prepare its validation, as I explained it before. And this is a part of my work. So, and for the CMB, I will let Amalia present the other instruments.
Actually, I think I don't
Sorry.
know if all of you. No. I just read. So as every launch of every instrument we are involved in and not, it's always very emotional and very exciting. And just anecdotically, very often we organize like meetings to watch the launch all together. And I remember specifically Euclid, we were all year at APC to watch the launch live, and it was very exciting, and everything went great. Luckily, it was very cool moment to share with our colleagues. Go on, Amalia. I'm sorry. Go on.
Yeah, so about the CMB, I've said a few times that we can observe these CMB photons today. So they cannot be seen by eye because over the past 13.8 billion years, as the universe has expanded, the wavelength of these photons has been stretched, and that has shifted them from the visible light to microwave radiation. So we can detect them with instruments that observe in microwave wavelengths. Several instruments have been built to observe the CMB over the past 80 years since it was first detected, both from ground and from space. And in particular, I'm part of the Simons Observatory collaboration, which is built for CMB telescopes in the Atacama Desert in the north of Chile at an altitude of 5,400 meters. So it was built so high because at such altitudes, you're less bothered by the atmosphere, which is very dry. So you're not so bothered by the emission of photons by the water vapor molecules that are contained in the atmosphere. So the Simons Observatory consists of two types of telescopes. We have one large aperture telescope, which we call the LAT, and then three small aperture telescopes, which we call the SATs. So the LAT is the one that you see on the top at the right, and then the SATs are the ones that you see at the bottom, these three smaller ones. The large aperture telescope is suited for observing small scales in the CMB. So it has a really large mirror, which is 6 meters in diameter. And so this large aperture basically provides the angular resolution necessary to distinguish the fine details in the CMB maps. So this telescope is mainly used to study gravitational lensing in the CMB, the distribution of galaxy clusters as well, amongst other things. And then the three small aperture telescopes, they're designed to study the largest angular scales of the CMB, which contain the information about the B modes that I was talking about before. So I work with these three smaller telescopes. One of the major challenges when observing the CMB is controlling contamination from ground pickup and from the atmosphere. So for the atmosphere, you want to be in a very dry place. And then to mitigate ground pickup, what you do is that you build this big shields around the telescopes, which you see in the picture on the left. So you actually don't see the telescopes because they're kind of covered by this shield. And then the LAT observes across different frequency bands, and then each SAT is dedicated to a different frequency range. And this allows us to map the sky over a broad spectrum. And then by combining the data from all three SATs, you have this broad spectrum, which is important to be able to separate the CMB from the foreground, since the emission of happens at different frequencies, basically. So that's the information that you use to separate them. And both, so the last thing I wanted to briefly mention about these telescopes is that they both rely on very sensitive detectors called transition edge sensor bolometers. So these detectors that are inside the telescopes, they're cooled to very, very low temperatures. And this is what allows you to minimize thermal noise and to achieve a very high sensitivity, which you need to observe the CMB. So you have to realize that these detectors are so sensitive that they can detect tiny fluctuations in the CMB temperature of the order of 0.00001 Kelvin. So they have to be really, really good. At this point, these detectors are so good that you can no longer improve the sensitivity of a single detector. So what you can do to improve the sensitivity of the instrument is to just stack more and more detectors. So each of the sats basically has an array with about 10,000 detectors, and then the LAT has an additional 30,000 detectors. So in total, you have about 60,000 detectors up there observing the CMB really with unprecedented precision, which is really cool. So these sats, they started taking data in April of 2024. So they've now been collecting observations for over 6 months. The first two started in April, and then the third joined just a few months later. And then the LAT is just beginning its observations right now, which marks a really exciting milestone in the whole Simons Observatory project. So now we have all these 4 telescopes which are operational, and we're starting to get all this data. So it's the focus of the collaboration is slowly shifting towards data analysis, which is really cool, which is what my group does. And so we have many more people across the collaboration that are starting to work to process and to interpret all this data that starts flowing in. So that's the stage that we're moving into right now, and that I'll be working on for the rest of my thesis.
That's very nice. Thank you. Thank you both. I would like to know if there are any questions. Joanna, did you want to ask anything, curiosity or something that wasn't completely clear? Otherwise, I have a couple. I want to be a bit nasty. And I want to ask, what if nothing works? I mean, what if after all this huge effort, we don't actually find a signature for inflation? Or what if in many, because these are a part of, obviously, what we're presenting today are a part of all the project that exists. But for instance, now I'm thinking about dark matter here at the lab. We also have some experiments that are trying to detect directly dark matter particles rather than the effects that they have. And what if we don't find anything? Because if we do, then it's all great. And we do have our theories. We know what we're looking, but what if nothing's there? What do you reckon?
Should I start, and then Anaïs, you can take over when you want?
Yes,
So
yes.
because I was very optimistic in what I was presenting, and I was saying we're going to measure R. Obviously, you never know how small R is, so you don't know if your telescope will be able to detect it. But what you basically do with these types of experiments, and what has been done already before, is that you build this telescope and you say, okay, I'm going to try to measure R. If R is this small, my telescope would have been able to measure it. So if we don't find anything, it doesn't necessarily mean that you can't measure it. It just means that R is smaller than this. And that already, so setting this kind of upper constraint on what R can be, can already be helpful because it can already allow you to discriminate between different models that might predict a value of R that is higher than your upper constraint. So at least you know, well, that model cannot be entirely correct because if R was that large, we would have detected. So I guess it's like either way, you have a scientific result, which is the nice thing about it. Yeah, that's what I would say for the CMB at least.
Yeah. Anaïs, do you want to add anything?
Yes, I agree with Amelia, but I think we can. So if we don't find anything, so we can. So first we can rethink of two another experiences, but it will be both expensive and very, very long, or we can rethink of for a new theory, but it will be very, yes, I don't know, but we will have to rethink the theory, or the theory of gravity, and then cosmology, standard model, and all of the things. So it will be very difficult, but I think it's a part of science and research in particular, because we are always trying to validate our models, and sometimes it doesn't work, but yes. But the particularity with cosmology is that the experiences are huge and very expensive. So, for example, I don't know exactly, but I think in biology or chemistry, experiences are very much smaller. So if it doesn't work, it's very easy to change your experiment. But here, it's it's very much more difficult, and so yes, we will see, I think.
I don't know if anybody else has any questions. I actually have two. And one came to me right now because Anaïs was mentioning it. Can you maybe tell us a bit more about this this collaboration dimension that is very typical of modern physics, and especially in almost every domain of astrophysics? Nowadays, we're talking of huge international collaborations. Can you tell us a bit more about this aspect, and also about how you like it, really, like what it brings, positives and negatives of working in a huge community? I don't know. We start from Anaïs and then we go to.
Okay. So for me, I work in Euclid, so it's a very, very good, huge, collaboration. It's a global collaboration with researchers from all over the world, and I think so for me, it depends, but I think for the positive aspect, so it's important to know that your work will be used by all the collaboration, and you are a very tiny part of a huge effort. So it's very satisfying, I think. And so in Euclid, I always feel like I'm useful for the work and the collaboration, etc. But for the negative aspects, it can be very difficult to find a place in the collaboration. So I have two friends who are doing their PhD in quantum physics. So with just one experience and one team, and their team, there are like 10 people in their team, so it's very small in comparison to Euclid, of course. And I think they interact more with their team, and of course I can't interact with all the people in Euclid, and sometimes it's very hard to know exactly who do this, and yes, to find a place in the collaboration, but it's a part of astrophysics and cosmology, as you said, Julia. So we are obliged to work like this, but yes, it's interesting. I That's
Amalia?
it for me.
Yeah, no, I mean, just gonna, I mean, everything that Anaïs said is obviously what I think too. I think it's really cool that these projects are so huge and they require many different types of expertise, and even just building the telescopes You need people making the mirrors and people being on the site. So I work for this Simons Observatory collaboration, which is about 300 people. It's an American collaboration, but then the site is in Chile, and a lot of the parts of the mirrors, for example, were built in Germany, and then the data science is done a lot in Europe and in Japan. So it's really all over the world, and I think it's really cool that you're forced to work with different countries, and it's not about the Americans or the Japanese or whoever discovering anything. It's really you're forced to work together in this very international environment, and which is not really a trend right now in the world. So it's good that we kind of preserve that, at least in research. So no, I really enjoy that. I really enjoy the international aspect of it. And you get to travel around a lot because you work with people all over the world, which is also quite cool. Yeah, so as Anaïs said, it's such a big group. You're constantly, which maybe people don't realize, that our job is also a lot of just being in meetings with all these people, because you have such a big group of people that communicating every result, it takes so many meetings to get the information across the collaboration. So you end up spending a lot of time in meetings. But I guess that's a very small drawback compared to all the advantages. Yeah.
I have one last question. If you were to advise, let's say, someone younger than you, why cosmology? Why did you choose cosmology? Why would you advise somebody to choose cosmology? Or maybe why not? So what I mean is, what do you feel are the things that should passionate you or that you should be interested in? You know what I mean? Like, what attracts you to cosmology, and who would you think would find it great like you do? Hopefully, I guess.
Do you want to start or shall I?
Go ahead.
So I don't know, it's difficult. I've always had this since I was really little, this kind of fascination for the universe and for kind of the biggest thing that exists. I don't know. So for me, I think it's not something that you choose rationally. It's just kind of this feeling of I really want to understand this. It was not a very rational choice in that sense. Yeah, so I guess in a way, if you want to do that, you will feel that need to understand that. I think also you have to be quite obsessive in a sense to do research. So I guess the people that go into this, they're also kind of, you have to have your head really set into, I want to understand this and go for it. Yeah, I don't know if that answers the question, but I guess that's.
Thank you. Anaïs?
It's a very difficult question, but I think yes, if you want to do cosmology, first you have to be very patient because you have to do a lot of physics, a lot of fundamental physics just to have the theory basics of cosmology, and it can be hard because when you are younger, when we think of astrophysics or cosmology, we think I don't know, of planets, stars, universe, and it's very and can be very very fun, I think. But in fact, you have to work a lot on theory, on computing science, and I think it's interesting also, hopefully, since I'm doing a PhD, but it could be at the beginning a little bit disappointing in comparison of all the nice pictures of stars, galaxies, etc. But at the end, it's very, very exciting to try to understand the origins of the universe and to work with objects. Like for me, I think it's very fascinating to work with objects like galaxy clusters because it's just thousands of galaxies together. I think it's a very, very impressive. So it's a very pleasure to work with this. but I can understand, like, I think liking cosmology and working in cosmology is very different, because if you just like cosmology, you can just do your own researches and like what is I don't know, a galaxy, what is the Big Bang, and if you but if you work in cosmology, you have to deal with a lot of computing science, and it's very important to know this. But I think it's a very interesting also, and I don't know if it answers the question, but
It does. I think it's a very good point to say that as any other job, you need to come in with a clear expectation of what you will do. I think you would agree, right? So it's clearly a job driven by passion, curiosity, but it does need how can I say, stubbornness almost, I want to say, and resilience. And obviously you need to know, because both of you in a way are let's say on the side of data analysis, right? And what data analysis really is, it is a lot of programming also, and computing, and right, and kind of refining your tools to analyze the data. However, I think it's important that we say that this is not the only job that exists in our domain, right? There are the people that did build the instruments that flew or that are on the ground, and there are the theoreticians with their blackboards and pencil and paper almost. And there are many different jobs, but I think it's a good advice that people come in, like students in physics, choose their path with open eyes on what they like to do on a daily basis, not just the beautiful pictures that come out at the end, because those are very rewarding, but they're usually at the end of long months of doing something else. And if you enjoy the something else, then it's great. And you need to come in with open eyes. I think this is very good advice. Okay, so if nobody else has any questions, I think that this concludes our 1 hour together. Does anybody want to ask anything or comment? Okay, if not, before anybody goes away, I would need to share my screen. Yes, thank you. Wait. Just wait a second. So I hope you see my screen. So just for the people that are coming in, and for the people that may be connected or that will rewatch this webinar on internet, please scan this QR code. It will lead you to a very brief questionnaire on your appreciation of this webinar. And this is incredibly useful for us for the future and for our PICO project to evaluate our work. So please do it. Don't hesitate to scan the QR code and reply to, there are, I think, 9 or 10 questions total. Okay, so thank you very much. I can stop sharing this. I would like to thank again Anaïs and Amalia for being with us. It was great. I hope that you all enjoyed it, that you learned a few things about cosmology, and see you all again next time. Thank you very much. Thank you.